Welcome to the Learn Security video training lesson on protocol and traffic analysis. In this video, we are going to take a look at the basics of the 802.11 protocol with a practical twist. As we already covered these aspects in the course slides, we will not dive into the protocol details, but instead, we will demonstrate how what we learned in theory also applies in real-world devices. In the first part of the video, you will learn how to configure your Wi-Fi adapter in order to enable monitor mode and traffic capturing. We will assume that you correctly connected your wireless adapter and loaded its drivers. You can verify this by running the iwconfig command in a terminal window. The output should show a selection related to your wireless card. On our machine, the wireless interface is called WLAN 0, as you can see. Now from the same terminal window, you should kill all the interfacing processes as the next step of your setup. To accomplish this, we use a very convenient functionality of AirmonNG. Launching AirmonNG tool with the check option will show these processes that may cause problems during capture. In our case, AirmonNG informs us to kill WPA_supplicant and Network Manager process to avoid conflicts. To stop both processes, we need to specify the kill option 2 on the command line. So now we can safely enable monitor mode. This is going to be easy. Just run AirmonNG start and specify your wireless interface name. From the output of the command, you will be able to determine the name of your newly created monitor interface. Typically, this will be called Mon0. But this may not always be the case, so double check the command results on the screen. You can verify everything worked as expected by rerunning iwconfig and checking if your monitor interface is there. We must take one little step to begin our traffic analysis. In fact, the monitor interface is listening on a particular frequency, which could be different from our test network. We must thus switch it to listen to traffic on the correct channel, which is number 11 for us. Type iwconfig mon0 channel 11 and run it to set the correct channel. Verify the option was set by running iwconfig once more. You will see it reports the wireless frequency using gigahertz notation. 2.462 indeed corresponds to channel 11's central frequency. Now we are set to go. To simplify this overview, we have set up our test access point to use no security at all. You will see how things change in the attacks video when encryption will be enabled. To start analyzing network traffic, fire up Wireshark. Ignore this warning dialog if you are using Kali as a super user like we do. Running Wireshark as root is a security risk, so don't do this in a production environment. You are advised to consult Wireshark online documentation, which provides instructions to run the software as an unprivileged user. When Wireshark is completely loaded, select Mon0 or whatever your monitor interface is named from the interfaces list and click on the Start button. Packets will flow very fast as wireless networks produce a lot of management and control traffic. To begin with, you should filter the capture, retaining only the traffic relative to your network. To do this, you will need the AP's MAC address. On most devices, you will find it written on the bottom side of the device. This time, we will try to determine it using only Wireshark. As you know, beacon frames are constantly transmitted by access points in order to advertise their presence to possible listening clients. So we only need to identify one beacon coming from our access point to get its BSSID value. To filter all frames but beacons, use this expression, wlan.fc.type_subtype == 8. Scroll down to the filtered beacons until you find one broadcasting your SSID value by looking to the last output column. If you inspect the frame headers, you will find the BSSID value. We want to copy it and write a new filter. First, we remove all the beacons as we don't need them anymore. Then we use the wlan.bssid property to focus the capture only on our network traffic. Apply the filter and you will be able to inspect your own network frames flow. Here you can see the results of applying the filter on our scan. We will now stop Wireshark capture for just a moment. In the next part of the video, we will analyze the authentication and association steps in the 802.11 protocol. For educational sake, we disconnect all the wireless clients from our network and remove their network settings. This will give you the opportunity to see each step more clearly. We've already disconnected the client devices, so if we reload Wireshark Capture, we only get an empty display as we are already filtering beacons. Let's try to turn the client back on. As soon as the wireless device becomes ready, we see probe requests and responses coming in. This is the result of our wireless client trying to determine nearby network's availability. As we have deleted any network configuration settings on the client operating system, the device does not try to automatically associate to the discovered network. To force the association process from the client machine, connect to your test network. Let's see what happens. Suddenly you should see a lot of frames coming in. You could possibly scroll through the capture and find the authentication association frames by inspecting it, but as an exercise, we will come up with a new filter expression to do just that. This will select only management frames. As you should remember, they have a type value of 0. We added a somewhat complex logical expression to filter management frames with 3 particular subtypes corresponding respectively to association and authentication frames. For the sake of completeness, you should remember that a subtype equal to 0 corresponds to an association request, while 1 is for association responses. All authentication frames are instead identified with the same subtype 11, the B number in hexadecimal notation. The tables from the slide will help you remember all of these number and subtype associations. Let's now examine the capture. The 4 initial frames exactly represents the standard authentication and association process. If we inspect the first authentication frame, we see that the source corresponds to the client MAC address. The frame is directed to the AP, as you can read from the receiver address field, which reports its MAC address. Drilling down, we discover Open Authentication System was used in the process, and given this is the first frame, its sequential number is set to 1. Authentication response frame is also identical, but as you can imagine, the sequential field has been incremented while source and address fields are obviously swapped. The status field, as in the previous frame, reports a success to indicate the wireless connection procedures can go on to the association phase. In the association request frame, our client is sending along some capabilities information like supported rates and channels. Those will be used by both devices to negotiate communication parameters. As the last step of the process, we can find the association response. This frame contains capabilities information too that are needed to negotiate throughput rates and other low-level communication settings. After association, wireless communications can now really start, so we should be able to see at least some data frames after all, but we need to delete a couple of filter conditions. And here you are. Data is flowing too. As we have no encryption enabled, we can see the frame payload in plain text. For example, we can pick an ARP packet sent by the wireless client. The content is indeed perfectly readable. This concludes our video presentation of wireless authentication and association processes. Along the way, you also learned how to use Wireshark tool to filter captured traffic and display only the information you really want to see. As you will discover, this is an important skill that will help you inspect and debug your attacks. Thanks for joining us.